Okay, so let's continue from where we left off at the end of last week. We were talking about increasing and decreasing functions. So let me just recall. We say function f is increasing on an interval I, an open interval or closed interval, if for any, and I'm going to underline the word any, x values, which I'll call x1 and x2 in I, where since the x-axis is horizontal, where x2 is on the right and x1 is on the left, f of x2 is greater than f of x1. F of x1 is less than f of x2. So the f values, these are the y values at x1 and x2. So this is like the y1 and this is like y2. So if I pick any two x values on the interval, so I have some interval I, open, closed, doesn't really matter. I pick any two x values x1, x2, not just the endpoints, could be anything in there. The y value at the right endpoint is always higher than the y value at the left endpoint, no matter which 2 points I pick. And as I cautioned you last time, the definition of an increasing function doesn't mention the word derivative at all. So when I ask you what the definition of an increasing function is, don't use the word derivative. You can say it in words if you want. You can say, given any 2 points in the interval, the point on the right has a higher y value than the point on the left. But don't use the word derivative. That being said, as I said last time, there is a theorem which connects derivative to the idea of increasing and decreasing, and we're gonna get right to that now. Let's see, what do I want to say first? So this one doesn't have a name. Let's let f be continuous on the interval AB and differentiable on the interval, the open interval AB. So now that you're all veterans of both the extreme value, now that you're all veterans of the mean value theorem, those hypotheses should look familiar. So let f be continuous on the interval, the closed interval AB, and differentiable on the open interval AB. So if the derivative is greater than 0 for all x in AB. Actually, I'm going to use the symbol for in rather than writing out the word. It's one that I introduced at the beginning of the semester, and I think we should get used to seeing it. For x in the interval AB, then f is increasing on AB. So if the derivative is positive everywhere inside the interval, then the function is increasing on AB. That doesn't mean that the definition of derivative involves, sorry, the definition of increasing involves the word derivative. It just says if the derivative happens to be positive at every x value between a and b, then this definition is true. If f prime of 0 is less than 0 for all x in AB, then f is decreasing on AB. So where the derivative is positive, the function is increasing. Where the derivative is negative, the function is decreasing. And this shouldn't come as a tremendous surprise. If f prime, oops, sorry, this should say f prime of 0. This should say f prime of x. My bad. If f prime of x is equal to 0 for all x in AB, then f is constant, just a horizontal line. So assuming the function is continuous and assuming it has a derivative, the sign of the derivative, positive, negative, or 0, tells us where the function is increasing, where it's decreasing, and where it's constant. Not all functions have derivatives everywhere. We know that not all functions are smooth everywhere. Absolute value of x fails to be smooth, fails to be differentiable at x equals 0. Now, I want to show you how the proof of this works. I'm going to show you the proof of 1. Once you understand the proof of 1, the proof of 2 and 3 follow exactly the same way. So we're going to assume.
Professor?
Yes.
Could you read 3 again, please?
Sure. If f prime of x equals 0 for all x in AB, f is constant on AB.
Thank you.
Sure. Is the image not as good as it normally is? Because it looks okay here, but I know once last week we were having Wi-Fi issues. Is it okay or not that good?
It's pretty rough.
It's a little grainy.
A little blurry, yeah.
Okay. I'll try to write a little bit bigger. It may be Wi-Fi issues again, but let me see if just writing bigger will fix that. One thing is if it does turn out to be Wi-Fi issues, since I'm recording this locally on my computer, once I upload it, the uploaded version should have, decent picture quality. But in the meantime, that doesn't help you. So again, I'll try to write bigger to get past that. Okay, so let's assume that these hypotheses are true. Let's assume f is continuous on the closed interval and differentiable on the open interval. So f is continuous on AB, and not only is the function differentiable, but its derivative is positive. F prime of x is positive for all x in the open interval AB. Now, what we're trying to do is show that this is true. We want to show that the function is increasing. We want to show that if we pick any 2 points, the point on the right is the higher of the 2. So let's see. Let's let x1 and x2 be anywhere in the interval AB where x2 is the point on the right and x1 is the point on the left. So we have some function. I'm not going to sketch it for you. We have this interval from A all the way up to B. And you pick any 2 points inside where x2 is the point on the right and x1 is the point on the left. Could be the endpoints, might be somewhere in the middle, who cares? Anywhere in this interval from A to B. Okay, so now we're going to, since we have the function is continuous on the closed interval and it's differentiable on the open interval, so having a derivative, that's what it means. Differentiable means not only is a derivative exist, but it's positive. But I don't care that it's positive yet. All I care is that it exists. I can use the mean value theorem because the mean value theorem just necessitates continuity on the closed interval and differentiability on the open interval. So by the mean value theorem, and I'm going to abbreviate mean value theorem MVT, by the mean value theorem, there exists an x value. We know what this says. There exists an x value, c, x equals c, somewhere between x1 and x2. So let me just write that. Oops, I don't know how that came out. Somewhere between x1 and x2. So c is somewhere between x1 and x2, such that f prime of c is f of x2 minus f of x1 all over x2 minus x1. So somewhere between x1 and x2, there is a c such that the derivative at c, the slope of the tangent line at c, is parallel to the slope of the tangent line, the slope of the secant line on the curve between x1 and x2. I'm going to do a little bit of algebra now. I'm going to multiply both sides by x2 minus x1 to clear fractions. And I'm going to switch sides. So I'm going to write the f of x2 minus f of x1 over on this side. So I'm just going to multiply both sides by x2 minus x1. So that just brings it next to the f prime of c. And then I'm going to switch sides of the equality, which doesn't matter. So f of x2 minus f of x1 is equal to, so this is equal to what I get if I multiply both sides of the equation by x2 minus x1. So it's f prime of c times x2 minus x1. Just a little bit of algebra. Now I'm going to look at the right side of the equation. So remember, we assumed that the derivative was positive everywhere between a and b. The c is certainly between a and b because it's between x1 and x2, and x1 and x2 are between a and b. So the derivative is positive at c because it's positive everywhere between a and b. So that is greater than 0. We assumed it was greater than 0. everywhere. So that's greater than 0. You can write a little plus instead of greater than 0, but however you want to write it. What about this term, x2 minus x1? If x2 is the point on the right and x1 is the point on the left, in other words, if x2 is bigger than x1, what's the sign of this term, positive or negative? If I take x1 and subtract it from x2, what do you get? A positive number or a negative number?
Positive.
Positive. So this was positive and this was positive. What do you get if you take two positive numbers and multiply them?
A positive.
Positive number. So the product of these two things, this whole thing, is greater than 0. So f of x2 minus f of x1 is greater than 0 because this was positive and this was positive. In other words, so let me just rewrite that. F of x2 minus f of x1 is greater than 0. In other words, f of x2 is greater than f of x1, or I could just as easily write that, and that's perfectly fine. But this is how I wrote it before, f of x1 less than f of x2. So in other words, the y value of the point on the right is going to be higher than the y value of the point on the left. And it doesn't matter which 2 points I pick. The y value of the point on the right is going to be greater than the y value of the point on the left. Therefore, the function's increasing. So f is increasing on AB. Because no matter which 2 points I pick, the y value of the point on the right is bigger than the y value of the point on the left. End of proof. At the end of a proof, we put a little square, a little filled in square. Just to let our reader know that we're finished with the proof. You start a proof with the word proof, you end a proof with a little square. Reading math isn't always the easiest thing to follow, so we try to make it easy as easy as we can. Try to make it as simple as we can. So proof of number 2, if it's, if the derivative is less than 0, looks almost exactly the same. The only difference is this is going to be negative, which means the product of that times that, since this is still positive, is going to be negative, which means the inequality is going to come out the other way around over here. The proof of number 3, this thing's going to be 0. If you take 0 and multiply by who cares, you get 0. And so f of x2 equals f of x1. They're at the same height. So the proof of 2 and 3 are almost identical. We just proved one. So the practical upshot of this is that if we happen to be in the nice situation where we have this nice smooth function, so not only is it continuous, but it's nice and smooth, we can use the derivative to figure out where the curve is going uphill to the right, where it's increasing, and where it's going downhill to the right, where it's decreasing. So in your professional lives, sometimes you will be dealing with functions which are nice and smooth, and sometimes you won't. It just depends on what application you're in the middle of. So sometimes this will be applicable, and sometimes you'll need stuff that we're not covering right now. But let's at least talk about the nice case where everything is nice and smooth. So how about we do this? Consider the function of x equals x cubed minus 3x. Let's find the largest open intervals upon which f is increasing and f is decreasing. So in other words, we want to figure out where the derivative is positive and where it's negative. So let's just start by taking the derivative. So you don't need to wait for me for that. You can easily take the derivative. This is a polynomial function. It's easy to take the derivative of polynomial functions. The 3 comes down. You write the x. 3 minus 1 is 2. Minus derivative of 3, minus 3x is going to be minus 3. And we want to know where that expression, for what values of x that expression is positive, and for what values of x that expression is negative. So let's go ahead and make a sign chart. This is going to be a sign chart for the derivative. We spent a lot of time at the beginning of the semester making sign charts, and I mentioned that you should tell me what function it's a sign chart for, and that's going to be obvious. The reason for that's going to be obvious in maybe by the end of today, or at least by next class, because we're going to have multiple sign charts floating around. But let's figure out where this thing is positive and where this thing is negative, so we don't have to solve this by algebra. We know that when we're making a sign chart, we start off by figuring out where the thing is equal to 0. So let's set f prime of x equal to 0. So 3x squared minus 3 equals 0. I can divide both sides by 3. X squared minus 1 equals 0. X plus 1, x minus 1 equals 0. So either x plus 1 equals 0, in other words, x equals minus 1, or x minus 1 equals 0, x equals plus 1. So at x equals 1 and negative 1, those are the two places where the derivative is equal to 0. So let's say minus 2. Yeah. So at minus 1, the derivative is 0, and at plus 1, the derivative is 0. Remember, those are not open circles, or those are honest to goodness zeros. And that breaks the derivative up, the real number line, up into 3 parts. Let's pick a point in each part, plug it into the derivative. Everything with this sign chart has to do with the derivative, and figure out where we have plus signs and where we have minus signs. So point to the left of minus 1, how about minus 2? F prime of minus 2 is going to be 3 times minus 2 squared minus 3. So that's 3 times 4. That's 12. Minus 3 is 9. I don't really care exactly what it is. I just need to know it's greater than 0, which it is. So at minus 2, it's positive. So at minus 3, it's positive. At minus 1.5, it's positive. It's positive everywhere to the left of minus 1. And if I plug a point in between my two endpoints, how about 0? Prime of 0. So 3 times 0 squared minus 3. That's negative 3, of course. And that's, oops, negative. So it's negative at 0, negative at a half, negative at minus half, negative 2/3. Anywhere between negative 1 and 1, it's negative. And I pick a point to the right of 1. How about 2? 3 times 2 squared minus 3. That's 9 again. That's positive. So it's positive over here. So this tells us where the original function is increasing and where it's decreasing. Where the derivative is positive, we know that the function is going uphill to the right, it's increasing. And where the derivative is negative, we know that the function is going downhill to the right, it's decreasing. So it's very common for us to put little arrows over top of these regions. We always put the arrowhead on the right. So over here, the function's increasing uphill to the right. I'm going to put an arrow going uphill to the right. Over here, between -1 and 1, it's decreasing. I'm going to put an arrow going downhill to the right. Again, the arrowhead always goes on the right. We always imagine we're moving from left to right on the number line. And then uphill to the right over here. So we are certainly in a position to answer the original question. So the function is increasing. I said the largest open interval, so I have an open interval to the left of -1, so negative infinity all the way up to -1. I have another one starting at 1 and going on. So on those two open intervals, the function is increasing. And it seems to be decreasing between -1 and 1. So I was definitely able to answer the original question. Let me ask you another question, and we're going to use the same piece of information that we've already sort of generated here, this sign chart. I'm going to ask you a question about the same function. Find all critical points. And let me remind you that a critical point is a place where the derivative either equals 0 or doesn't exist. This function has no places where the derivative doesn't exist. So if it's going to have any critical points, the derivative is going to have to equal 0. Find all critical points and state whether each is a relative maximum a relative minimum, or neither.
Do you want us to speak up or?
Am I? Yes, if you already have an answer, please.
Okay. Well, wouldn't it just be -4 and 0 are the critical points because that's where it changes direction?
-4 and 0?
Yeah.
Maybe, are you looking at this?
Yes.
And where does it change direction? At -4 and 0?
Yes.
Uh,
Or maybe I'm mistaken.
It might be because the picture is fuzzy. Are you saying it changes direction at these 2 points? Oops. At this point and that point?
And 1. Wait, oh, that's -1 and 1.
Yeah, -1 and 1.
Okay.
Yeah.
Sorry.
No, it's okay. I think this is, I'm sorry that the picture is not very clear, and I was trying to write bigger, but apparently I'm not writing big enough. So yeah, morally speaking, you're exactly right. At these 2 places, this one is -1 and this one's at 1. So you're exactly right. So we have a critical point at x. So critical points at x equals -1 and x equals 1. Now, at x equals -1, this first one, are we at the top of a hill, which would be a maximum? Are we at the bottom of a valley, which would be a minimum? Or are we at neither of those things? Can you tell by the arrows? So over here, we're going up. and then down, what's going on at -1?
It's a maximum.
Yeah, it's a maximum. We're at the top of a hill. If you sort of are going up for a while and then you're going down, the place where you stopped going up and started going down, that's the top of a hill. That's a maximum. So this is a relative max. Relative maximum. And what about at 1? What's going on there?
It's a minimum.
It's a minimum. Before I go on, does everybody see how the plus signs and minus signs and the up arrows and the down arrows basically? Oh yeah, I see how fuzzy that is. Okay, I will do my best to write bigger, especially at the top part of the board. Does everybody see how the up arrows and the down arrows give you the basic idea of the shape of the curve, so you can see where you're going up, where you're going down, and where you hit like maxes and mins? Awesome. You get a lot of information from the first derivative. By the way, this business of looking at the first derivative sign chart and seeing where you have maxes and mins or neither, that's what the first derivative test is all about. That's all it is. Looking at this picture and discerning the shape of the curve. Let me just sketch what the curve looks like. Not that we really have all that much. We don't have quite enough information to be able to do this yet, but let me just show you how nicely the curve sort of echoes what we have right here. So if I'm going to put my y-axis down, I'm going to put it right under 0 because the y-axis is at x equals 0. And let me put the x-axis over here. I'm just going to -3, -2, -1. I'm going to have these line up as best I can. 1, 2, 3. Okay, smush this a little bit. Whatever. Even though we're not quite in a position yet to be able to sketch an entire graph based on the information we have, we can at least figure out where it crosses the x-axis. So we can find out its x-intercepts. That we could do without calculus. That's just algebra. So for the x-intercepts, we'll just set y equal to 0. And y, of course, is equal to f of x. So we'll set y equals 0. So x cubed minus 3x, the original function, set that equal to 0. You can do this however you want. I'm going to factor out my x. X squared minus 3 is equal to 0. And that means either x equals 0 or x squared minus 3 equals 0. I'm going to do a little bit more factoring. You don't have to do it this way. But I'm going to write x squared minus 3 is x minus root 3 times x plus root 3. Since it's kind of a difference of squares, if you think of 3 as a perfect square, if you think of 3 as the square of root 3, in which case x either equals 0, root 3, or minus root 3. So that's where my original curve crosses the x-axis at minus root 3 and at root 3. So at those 2 points and at 0, the curve crosses the x-axis. So the original curve actually looks a lot like this. That's what x cubed minus 3x looks like, more or less. You can see my picture is a little bit sloppy. That bump and that bump should be the same height, sort of one's up, one's down. They don't quite look like that on my picture. We'll get a better picture later. But you can see that we have a top of a hill at x equals -1. Basically what these arrows indicate. These arrows said go up, then go down. That's exactly what's going on there. And we have the bottom of a valley at x equals 1. Down and up. So those up and down arrows tell you a lot about the shape of the curve. Let's just do one more before we go on. let's do a curve whose shape we know before we even start. Let's let f equal x cubed. I know you know what the x cubed curve looks like. And again, let's find the largest open intervals on which f is increasing and decreasing. Basically, same question. And based on your prior knowledge, you should know the answer to that. But let's see what happens if we use the same methodology. So we're going to take the derivative. Super easy one to take the derivative of, just one application of the power rule, 3x squared. And we're going to build a sign chart, so let's set f prime of x equal to 0. So 3x squared equals 0, x squared equals 0. If we divide both sides by 3, in other words, x equals 0. Make a sign chart. And the derivative is 0. Oh, sorry, this should be f prime. We're making a sign chart for f prime. Derivative should be 0 at x equals 0. And let's pick a point to the left of 0 and a point to the right of 0 and plug it into f prime. So f prime of -1 is 3 times -1 squared. That's 3 times 1, that's 3. It's positive. And f prime of 1 is 3 times 1 squared. That's 3. That's also positive. And I can put my up arrow here and my up arrow here. Now, before we answer the question, let's just go ahead and sketch the graph, since we happen to already know what the graph looks like in this particular case. You know what the y equals x cubed curve looks like. It kind of looks like a right side up parabola to the right of 0 and an upside down parabola to the left of 0. And you can see how these arrows echo the shape of the graph. We're going uphill to the right here. We're going uphill to the right here. For just an instant, the tangent line is horizontal. Now, find the largest open intervals upon which f is increasing and decreasing. It's very, very tempting to say that the function is increasing on -infinity to 0, and it's also increasing on 0 to infinity. Those are certainly true statements. The function is certainly increasing over here, because if I pick any 2 points on the curve, the point on the right is the higher of the two. And it's also true that if I pick any 2 points over here, the point on the right is the higher of the two. So it's certainly true that the function is increasing on that interval and increasing on this interval. However, I asked you to find the largest open interval or open intervals upon which the function is increasing. Can somebody tell me why these two, while they are intervals where the function is increasing, are not the, it's not the largest interval where the function's increasing? Give me a larger interval where the function's increasing. Something that's bigger than that and that.
It's increasing negative infinity to infinity because
Yep.
it's never decreasing. It just levels out for a sec.
Yeah, it's not only is it not decreasing, but so you're totally right, and I heard more than one voice there, and I assume you all had that same answer. It's actually increasing from negative infinity to infinity because if I pick any 2 points, say this point and this point, or this point and that point, or that point and that point, the point on the right is always the higher of the two. Remember that the definition of increasing doesn't involve the word derivative. So the fact that the function has derivative 0, for an instant, doesn't change the fact that the function's actually increasing on this entire interval. So the answer to the question is that the function is increasing from negative infinity to infinity. It's increasing on the entire interval. So be a little careful if you have one of these functions which has a derivative with the same sign and a 0 in the middle. It's actually increasing, or if those were both minus signs, it'd be actually decreasing on the entire interval there. What if I said state?
Wait, Dr. Order,
Oh, yeah.
I do have a quick question.
No, please.
So on the homework, we had a problem. It was like find all the critical values of the function, and it was
Yep.
one of these functions. And wouldn't the critical point be at 0 for this function?
Absolutely, it's 0.
Okay.
Yeah,
'Cause
sure.
I'm almost positive I put that on the homework and it said I got it incorrect, but
Okay. It could be a problem with my homework.
Okay.
I mean, I might have just made a mistake. What's that?
sorry, my niece is in the room and she was
Oh.
talking. That wasn't me.
He's more than welcome to the class. No, it's all good. So yeah, let me check the homework. If it's giving the wrong answer, that could just as easily be my fault. So let me go. Especially if anybody else had had the same problem, let me know, and I will definitely go check and see if I made a mistake somewhere. Because if I just put the wrong letter in the answer key, it's going to say it's wrong, and I just made a little mistake somewhere. So what if I said state all critical points? You just told me there was one at x equals 0. And say whether each is a relative maximum, a relative min, or neither. And you just said there is a critical point at x equals 0. That's where the derivative equals 0, and there are no places where the derivative doesn't exist. What kind of critical point is it x equals 0? Is it a maximum? Is it a minimum? Is it neither?
Neither.
It's neither. It's not at the top of a hill, and it's not at the bottom of a valley. So if you have like on your sign chart for your first derivative, you have plus, 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 minus, 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 uphill, downhill. This is definitely the top of a hill. If you have something like minus, 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 plus, 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 down, up, this is definitely the bottom of a valley. So maximum, minimum, but this one's neither. It's not at the top of a hill, and it's not at the bottom of a valley. Any questions?
I have a question.
Yeah.
Okay, so if like working with like if we had like three, I don't know if this makes sense. Okay, if we look at like the one like the sign chart we did before,
Uh-huh.
and it was positive on one side of the zero, and then it was negative, and then it was positive again. If it
Yeah.
was positive, positive, and then negative,
Uh-huh.
would that -1 just be neither because it's positive on both sides?
Well, if I understand what you're saying what happens if we have a situation like this? So we have this sign chart and we have a couple of critical points, and so it's positive and then positive and then negative. Is that what you're saying?
Yeah.
Okay, so we have two critical points. It's going uphill, uphill, and then downhill. What can you tell me about this second one? Is this a max, a min, or neither?
A max.
It's a max because we're at the top of a hill. You can see that from the arrows. What can you tell me about this one? Is it the top? Is this at the top of a hill?
No.
It's not at the top of the hill, so it's not a max. Is it the bottom of a valley?
No.
Nope. So it's neither. So
Okay.
this one's going to be a max. This one's going to be neither. Let me sketch you a curve that might have a shape like this. It could look like this. It could be going uphill, flatten out for a second, then keep going uphill, and then start going downhill. So it could easily have a shape just like that. I could write a curve that has exactly this shape. Does that make sense?
Yeah.
Okay, awesome. Any other questions? All right, well, in that case, I will see you all on Wednesday. Have a good one.
Thank you.
My pleasure.